Alright, so in this video I'm gonna be explaining a very beautiful article about domain generalization. The title is Improving Domain Generalization with Domain Relations. Just like relation extraction, there is a relation between two entities in the task of relation extraction. Here, I think they draw their inspiration from this idea in relation extraction. But they do it for domain, the relation between domains, not between entities, so that it could be useful for domain generalization. So distribution shift presents a significant challenge in machine learning, where models often underperform during test stage when faced with a different distribution than the one they were trained on. This paper focuses on domain shifts which occur when the model is applied to new domains that are different from the ones it was trained on, and propose a new approach called D3G. Unlike the previous methods that aim to learn a single model that is domain invariant, D3G leverages domain similarities based on domain metadata to learn domain-specific models. Concretely, D3G learns a set of training domain-specific functions during the training stage and reweights them based on domain relations during the test stage. These domain relations can be directly obtained and learned from domain metadata. Under mild assumptions, we theoretically prove that using domain relations to reweight training domain-specific functions achieves stronger out-of-domain generalization compared to conventional averaging approach. So in this paper, they consider the problem of predicting the label based on input feature. Given training data distributed according to P, we train a model F. We train this F parameterized by this theta using this loss function. Traditional empirical risk minimization is like this. The trained model is evaluated on test set from a test distribution, but when distribution shift occurs, the training and test distributions are different. So our objective is to address domain shift by harnessing the power of domain relations, which encapsulate the similarity or relatedness between different domains. To illustrate this concept, we focus on the protein ligand binding affinity prediction task, where each protein is treated as an individual domain. So this is beautiful. Each protein is treated as individual domain. Domains are considered related if they exhibit similar protein sequences or belonging to the same protein family. To formalize these domain relations, we introduce an undirected domain similarity matrix, where each element quantifies the strength of the relationship between domain I and J. So we derive the domain relations by leveraging domain metadata, which depict the distinctive properties of each domain. So this is an illustration. You see in A that the multi-head architecture, each training domain is associated with a single head for prediction. And in B, you see this relation extraction. You see the relation extraction module where fixed relations are extracted for domain metadata and refined through learning from the same metadata. And in C, you see that the training stage where X represents a single example from domain D, And the loss is composed of both a supervised loss and a consistency loss. And indeed, we have a test stage finally where the weighting of all trained domain-specific functions is used to perform inference. So the training stage. During the training, our approach utilizes a multi-headed neural network architecture. We denote the prediction by the D's head as FT, and HD represents the domain-specific head for domain D. E represents feature extractor. Our objective is to minimize the predictive risk for each data point when using the corresponding head, ensuring accurate predictions with each domain. This is achieved by minimizing the following loss function. In certain scenarios, some training domains may contain limited data compared to the overall training set, posing difficulties in training domain-specific predictors. To address this challenge, we leverage the assumption that similar domains tend to have similar predictive functions. Building upon this assumption, we introduce a relation-aware consistency regularizer. For each example within a training domain D, the regularizer incorporates domain relations to weigh the predictions generated by all training examples except the corresponding predictor. So this is an example, this is the formulation of loss. We call it relation-aware consistency loss. And A here is just the strength of the relation between domain I and D and J. The strength between D and J is this, A sub DJ. This loss encourages the ground truth to be consistent with the weighted average prediction obtained from other training predictors using the domain relations to weigh their contribution. By doing so, the regularizer encourages the model to rely more on predictions made by similar domains and less on predictions made by dissimilar domains, strengthen the relations between predictors, and help train predictors for domains with insufficient data. So to incorporate the consistency loss, we add it to the predictive loss in equation 2 and obtain the final loss. During the test phase, D3G constructs test domain-specific models based on the same assumption that similar domains have similar predictive functions. Concretely, we weigh all training domain-specific functions and perform inference for each test domain by weighting the predictions from corresponding prediction heads. One potential issue with directly collecting domain relations from fixed domain metadata is that these fixed relations may not fully reflect accurate application-specific domain relation. For example, geographical proximity can be used in any application with spatial domain shift, but it is hard to predefine how strongly two nearby regions are related to different applications. To address this issue and define and refine the fixed relations, it proposed learning the domain relations from domain metadata using a similarity metric function. Specifically, given domain metadata M sub I and M sub J of domain I and J, we use a two-layer neural network G to learn corresponding domain representations. So you see we can compute the similarity between domain I and J. So this is the similarity between I and J. And this is just the Hadamard product. And R is over, summation is over the number of heads, because each head is one domain. We use weighted sum to combine the fixed and learned relations. Finally, the relation is just a linear combination of fixed and learned relations. And then they give the theoretical analysis of that. But the algorithm is like this. We first, they require that the relation combine coefficient, loss balance coefficient, lambda, metadata, and learning rate are fixed. Then we initialize all learning parameters. So they extract fixed relations here. So this is fixed. Then they go through this convergence loop and then compute learned relations. So this is fixed relations, this is learned relations. And we know the linear combination of them could be useful for the loss. So if the loss function L is Lipschitz, then for a test domain, we have a beautiful upper bound. And then they have another proposition under the conditions of the theorem that I told you. Suppose A sub ij is 1 and consider the function class. Define the excess risk with similarity matrix. Then we have this upper bound for the infimum of supremum of your risk. So these are examples. For example, there are fixed relations. We know that Saudi, right, and there is a fixed relation between them. But the learned relations is what you are training.